Hi, my name is Enrique Nueve, and this is my presentation for Theory of Computation Fall 2022. The title of my presentation is Symbolic Dynamics in Regular Languages. Here's the outline for this presentation, an intro, talk about some prereqs in graph theory, what are shift spaces, this core idea in symbolic dynamics, finite shifts in graphs, how do shift spaces and graph theory go together, suffix shifts, which is what is a particular type of shift space that corresponds to a particular um, type of regular languages, which we are going to show how they're related, and a conclusion to just wrap everything together. Let's provide some motivation for this talk, okay? What is symbolic dynamics? Symbolic dynamics is used in multi-dynamical systems in a discrete form via symbols over bi-infinite sequences where the symbols express states. Symbolic dynamics has been used for information theory and automata theory and other applications where dynamical systems is used. As mentioned earlier, this talk will cover the basics of symbolic dynamics and how symbolic dynamics can be used to express particular regular languages. And we'll also conclude with saying, okay, now that we presented all this material, why would we even want to do this? Why can't we just present a regular language, in a simpler way with like a regular expression or with a finite automata? But we'll get to that and explain why. Okay, before we can actually get into the core topics of this presentation, we need to do a quick review in graph theory. Symbolic dynamics highly relies on graph theory. As the slide shows, we're going to let a graph be denoted by G, which is a pair of vertices and edges. We're going to say that an edge, we can have edges that are directed or undirected. This shows here the notation we're going to use, where if you give me an edge and it's from a direct graph, you can tell me what the initial vertex is from the first slot in the pair, and the second one is the terminal vertex. There's this notation here where I don't actually know we're going to need this necessarily. I think it actually didn't make the final cut, so I'm going to skip that. Furthermore, we have an adjacency matrix where we can just equivalently express a graph via matrix form, which shows, what are the edges from the different vertex in the graph. This is a little bit more unique. These terms, the nth power graph and the adjacency matrix of an nth power graph, let G be a graph. This should be if n is greater than or equal to 1. We define the entire power graph G of n of G to have vertex set Vg to the n, which is equal to Vg, and with precisely one edge from I to j for each path in J of length n from I to j. So this is all this definition is saying is the higher power graph is like, what are the edges of this higher power graph? If you have two vertexes, and let's say you have the fifth power graph, it just means that there will be an edge from the two vertexes if the initial graph has a path from said vertexes that's a length of 5 or whatever, nth. Next result is saying the adjacency matrix of the nth power graph. If you take the adjacency matrix and then take it to the nth power, or if you take your graph, take it to the nth power and then take the adjacency matrix of it, you get the same thing. This idea of is highly used is that isomorphisms on graphs, a bit technical, long definition, but what it's really saying is it's a type of bijection between two graphs where you preserve edge and vertexes. Here's a nice visual example of an isomorphism between two graphs in the following source. As you can see that, they're different shapes, the edges look different, the vertices instead of an A in graph G has an A, graph H has a 1, but you could still, if given graph G, you can construct graph H, and with the isomorphism, and also with the isomorphism from H, you can construct G. So yeah, that's about the extent of graph theory we're going to need. Let's get into shift spaces. What are shift spaces? I feel like the core idea in symbolic dynamics. Reading first off the technical definition, the set of bi-infinite sequences over A, script A, and finite alphabet, denoted by script A to the integers, is called the A full shift. This is a collection of all bi-infinite sequences. A bi-infinite sequence is just 0, 1, 2, 3, 4, 5, etc. to infinity, 0, -1, -2, -3, -4, -5 to negative infinity, both directions. So like a sequence, but both ways. And furthermore, a sequence is traditionally a sequence is a mapping from the natural numbers to some other space. And this space for us, this bi-infinite sequence is all integers mapped to some characters of a finite alphabet. We call the elements of the full shift, these bi-infinite sequences made up of symbols from the alphabet, points. For somewhat of intuition, points within the full shift can be thought of as trajectories of transitions through a system over infinite time. Because you go both to negative infinity and positive infinity, you can just go backwards in time, forward in time, and each step you take through it, each character, that each symbol on say bi-infinite sequence corresponds to some description of a state within our system. Here are some terminologies that go with shift spaces: a shift map, a mapping from the full shift to full shift, such that for any point in the full shift, y is equal to sigma x, whose ith coordinate is yi equal to xi plus 1. Although not too intuitive, all this is if I have a bi-infinite sequence, let's say this is my 0 coordinate, I apply the shift map, it's just going to map me to another bi-infinite sequence where everything is moved over by 1. That's it. We'd say a set of bi-infinite sequences is shift invariant if you apply the shift operation, the shift map, to the whole set of bi-infinite sequences, and you still get the same thing out. So although you move everything by 1, there's this like closure property under this operation. Furthermore, a shift space in general is the following. A shift space on the alphabet A is a shift invariant subset of the full shift, which is closed in the topology. Moving forward, we need to somehow, okay, now that we've introduced these bi-infinite sequences, these shift spaces, like how are we getting back to languages, which is, symbolic dynamics, regular languages, the topic of this presentation. So I'm going to start working towards that. As it says, for our purpose, there's a more intuitive way to define shift spaces via blocks, otherwise known as words that we're familiar with. A word V is a factor of a word T if T is equal to UVW for some words U and W. So you could think of this as like a subword, for example. So that's all a factor is. That's the common terminology in symbolic dynamics. There's a particular set of factors that are interesting. We'll define what they are. Set of forbidden factors. For a set W, some set of words, whose elements are called the forbidden factors, we denote by X superscript W the set of bi-infinite sequences such that no W is a factor of X. But what does that like really mean? We'll get into that. It turns out by using this definition of forbidden blocks, we can define a shift space, okay? So this is the alternative definition. Let F be a set of blocks, words over the alphabet, and let the shift space be elements of the full shift such that nowhere along any of these bi-infinite sequences we will find a word from said for some forbidden block word within the select block of words. That's all it's saying. So hopefully through some examples, we can get a better intuition of this. Let's say the set of forbidden blocks is the empty set. Well, then the shift space is equal to the full shift because we're not restricting anything. Let's say our set of forbidden blocks is the string 1, 1. Then the shift space that corresponds to it is all bi-infinite sequences such that no 2 consecutive ones are present. This is referred to as the golden mean shift. We're going to assume our alphabet is like 0 and 1. So you would have like 1, 0, 1, 0, 1, 0, 0, 0, 1, 0, 0, 1, something like that, but never will you see 2 ones in a row on these bi-infinite sequences. Here are some more operations we need to introduce so that we can actually get some of the further results. We're going to introduce an idea called an in blocks. Let x be a shift space over the alphabet, and let a superscript n subscript x be equal to b of an x be the collection of allowed in blocks in x. We consider ax to n as an alphabet as its own right. Furthermore, I can tell now there's a mistake here. What is an in block? An in block is any subword within any of the points, Bioinfinite sequences within the shift space. That's it. It's the union of all of those, of length n. So what is an nth higher block code? It's an idea that gets used a lot in symbolic dynamics. Well, nth higher block code is just a mapping from your shift space to a new shift space where you replace elements of the symbols within the original shift space with different symbols, concatenation of in-length symbols from the original space. It's a bit of a mouthful, but hopefully we can carry on as a description here. Thus, n replaces the ith, this should be beta vin, the entire block code here, replaces the ith coordinate of x with the block of coordinates in x of length n, starting with position I. We can define a entire block shift by x to the n as just the image of applying the entire block code to the whole shift space. Okay, let's try to get into languages of shifts. I'm going to try to convince you that there are languages that go along with these shift spaces collection of Bioinfinite sequences. Here's the definition. Let x be a subshift of a full shift, and let b of n denote the set of all n blocks that occur in points in x. The language of x is the collection as follows, which is just the union of all blocks of all lengths. So yeah, moving forward. This is interesting. It seems like this language for shift space is very large. It can be, and there's a lot of repetition or subwords and words, and that's true. But in particular, we're going to explore what are like the core properties of languages of shift spaces. This is going to be needed later to connect back to regular languages. As you can see here, we have languages of shift spaces are closed under subword and prolongable. The following properties of languages of shift spaces. The first one is our most important one, which we will do the proof on. Let x be a shift space and the language be equal to the union of all blocks of all lengths. Be its language. If a word is in L, then the first part is every subblock of W belongs to L, and B, there are non-empty blocks U and V in L, so that give me a word. There are two other words in language you can put on either side, which will make a larger word also in the language. And yeah, let's work through this proof. The other two results are important, but I think we can actually skip them for the time being. I'm not certain they're needed. Okay, so here's the proof for part one. If we have a word in the language, well, clearly it's in the union of all blocks, then a W occurs in some point X in X, because that's just what it means to be a block, the union of blocks over the said shift space. But then also every subblock of W also occurs in X, so it is in L. Just by de facto, if W is in L, if it's in some point in X, then anything in between is also in said point. Moving to part B. Furthermore, there are non-empty blocks U and V such that UWV occurs in X. Why is that? Well, these are Bioinfinite sequences, so wherever W is, there has to exist something on the other side. It's just because they're Bioinfinite sequences. So by construction, there are also there exist two words where if you can concatenate them to either side, it's also in the language. This is the proofs for part 2 and 3, but I'm going to skip those for the sake of time. Okay, so now that we have shift spaces, we need to look at a particular type of shift spaces called finite shifts or shift of finite type. As the definition says, a shift of finite type is a shift space that can be described by a finite set of forbidden blocks. In other words, a shift space X having the form X subscript F for some finite set F of